First of all, thank you all for being here in person, and thank you for those folks online right now. Very pleased to introduce our visiting speaker who's here this week with some great RAL collaborations, Dr. Brian Quaife from the Florida State University, and he's an associate professor there in the Department of Scientific Computing. So very interesting research areas. He comes from the background of applied mathematics and fluid dynamics. I was looking through his work. He does integral equations, numerics, and PDEs, which is really cool. And has recently done a lot of great work as well on wildfires. So great connections to RAL in multiple ways. Just a little history on Dr. Quaife is prior to the Florida State. He was a postdoc at the University of Texas, and his prior roots were in Canada, where he obtained a bachelor's in pure and applied mathematics at the University of Calgary, and then where he also got his applied math master's degree in 2006, and finally finished his PhD in 2011 at Simon Fraser University in Canada as well. So very pleased to have you here. I'll let you take over.
Sure, thank you. All right, well, thanks so much for that introduction. I'm impressed that you dug all that up. Okay, so thank you all for coming. In particular, Pedro for hosting me this week. It's been a productive few days. I've been able to reminisce about some of the days that I used to think more about level set methods, and we've been able to solve some problems, which has been a lot of fun. So yeah, I'm going to talk today about a variety of different projects that we've been working on at Florida State University. So the title is Innovations in Fire Science, Fluid Dynamics, Data, and Emerging Computational Methods. So I won't spend too much time on any one project. It'll really be kind of a survey of a variety of projects. So yeah, my home department is scientific computing, but I'm also affiliated with the Geophysical Fluid Dynamics Institute, which is also at Florida State. This is where the fire science program lives at Florida State University, as well as some other geophysical type flows. It's a really interesting department or institute with a long history actually in geophysical flows. And of course, this work is not all done by me. I put the members of my group on there. So Darren Sagel's a recent graduate. Jamaica Greenwood is a current PhD student who is here in the room and visiting NCAR this summer. And then Shin Tong at the end there was a previous postdoc. And then this work's been supported by NSF, the Department of Defense through CERTUP, and then some internal money at FSU. And so on the right here, this is a picture of me and the authors of the talk are all there, as well as some other colleagues and their group members as well. That was at the Jones Center at Itchawaway in South Georgia. And I'll show some other, we'll see some movies and pictures from there as well as we go. Okay, so I'd like to start with this slide, and I don't know if the audio will work. If it doesn't, it doesn't matter. There's not really much to hear. So I saw this YouTube video a couple of years ago when I was doing my sabbatical in Australia. And of course, it kind of piqued my interest right away about what was going on here with this guy's kind of amazing fire suppression system that just instantly detects when there's fire popping up on his property and then starts to spring water out at it. And so, of course, it's a big farce. It's a commercial for an insurance company that's saying, until this day comes, we'll be there to help you out. But I like it because it kind of gives us this idea that, there must be ways that we can improve this issue that we have with fire every year. Okay? And one of the ones that we focus on a lot at Florida State University is prescribed fire. Okay, so a lot of the stuff I'm going to talk about today, or I think pretty much all of it, is at prescribed fire scale. So don't think about the big fires that we see out west or even here in Colorado all the time or every season. Think of small scale prescribed fires that are used as a fire management tool. Okay? And so we've been fortunate to be able to go to some land conservatories. So that's the Jones Center with the video playing there. Tall Timbers, this is just a little bit north of Tallahassee. I go up there on a regular basis to work with collaborators up there, and once in a while we get to put fire on the ground. And so this was a big burn consortium that we did about 4 or 5 years ago. And so these are showing one of the main benefits that people think about when they think about prescribed fire. You're removing the litter that accumulates on the ground with time, and if you don't remove that, when inevitably you do get a spark, right, which is going to happen, then you end up with the out of control fires. Okay, so this is kind of the the thumbs up situation. The thumbs down is when you see something like this. This is somewhere out in California. Okay, it's not we're not alone in the U.S. with this problem. That's I believe that's in Greece. And then that one is in Australia. You can see the poor kangaroo silhouette there jumping in front of this building. So that's from the Black Summer in, I think, about 2019, 2020 is when that happened. Okay. So that's kind of maybe the main benefit people think about for prescribed fire, but it's certainly not the only one. Okay. So another big one that we think about a lot is removing invasive species. So this is again at the Jones Center, and this is showing a piece of the land that actually had not seen fire in quite a while. And this has resulted in all this kind of shrub and all these hardwoods that are not native to that area coming up in the bottom. These are longleaf pine forests. They're not supposed to look like that. What they're supposed to look like, and this is just like half a mile down the road, they're supposed to look like that. Okay, so nice longleaf pine trees and then wiregrass across the bottom. They put fire through this unit maybe every 2 to 3 years, and that keeps it looking like that. And using fire to promote species that are native and get rid of ones that are not isn't something that's new knowledge. This has been known by our ancestors forever. And again, when I was in Australia at their National Museum, I saw this exhibit about this was an indigenous group of people in Tasmania that were using fire for promoting their native grasses and wildflowers that are native to that area. Okay. So that hopefully, motivates why prescribed fire is why it's important, why we're motivated to think about it. And so now I'll just start kind of going through a variety of different problems that we've looked at. And so the first one that I'll talk about was, this is actually very early on in the program. The program is only about 8 or 9 years old, and because we're thinking about prescribed fire scales. These are very low intensity fires. And so one of the factors that we think really drives how fire moves is how air flows into and out of the fuel bed that's on the surface. And in the southeast for us, that's pine needles. Okay? So we wanted to be able to make measurements about the flow in and around a pine needle fuel bed. Okay? So the obvious thing to do is put it in a wind tunnel, but the issue was that as soon as you put it in a wind tunnel, it all starts just blowing away, right? So we needed some method to be able to have something that looked or had, say, the same characteristics as pine needles, but wouldn't blow away. And I had a student that was an expert in 3D printing, and so he 3D printed these structures that you're seeing here. We had 3 different porosities. That's what you're seeing here coming across the bottom here. Okay? 3 different porosities, just at different angles. Okay? And we put these inside of we first started with a small wind tunnel. That's what you're seeing there in that one, I guess, listed panel A. And we measured the wind velocity using a hot wire anemometer at a bunch of different heights. Okay? And this wind tunnel was also low enough it was small enough and low enough intensity that we did put pine straw in there as well. And we made some measurements about the velocity right down into the actual fuel bed. So when you're looking at the plots on the right here, this is showing you the velocity as a function of height. 1 is representing when you're right at the surface of the fuel bed. So you can see we measured it right down into the fuel bed and then up above it. This paper, one of our colleagues is a meteorologist, and I'm not going into the details here, but she was able to kind of explain some of these types of profiles that we see based on some of the classical meteorological models that this community uses. Okay? But this is kind of a small scale problem, and we're only getting point measurements with this hot wire anemometer. We wanted to really scale this up. So we went over to engineering at FSU, and we put it inside of a wind tunnel where they have a PIV setup. So there's going to be strobing going on here. And so here's the PIV setup. And so you can see at the bottom there, you can see a collection of those 3D printed structures down there. And we're making measurements of the velocity along that laser sheet that you see shining there. Okay, that's how PIV works. Okay? So you end up getting, on the right there, that's showing actually the data, the raw data that's coming into you. But after you put it through kind of the PIV, magic or PIV analysis, you end up getting a nice velocity field, across that entire laser sheet. And on the left there, I'm plotting the magnitude of that velocity field. and you can see, for instance, you can see the porous structures there at the bottom. Okay, then we have no velocity there. And then you can start to see, you can see a wake breaking, we can measure sweeps and ejections, all these kind of classical things that, that we think are important for understanding how air gets into and out of the pine straw fuel bed and therefore propagates the fire. Is that a question? Yeah.
Question. How do you normalize? What's the normalization?
That's a good question. The normalization, I think, was just against that number UB you see on the top, which is 1 meter a second. Yeah, yeah. Okay, so I think, yeah, that's it for that problem. So I'm going to talk a couple slides now about work that we are, continue to think about for embers. And so, so embers are sometimes referred to as firebrands, are of course one of the main ways that fire is able to propagate from, through, for instance, from the WUI, so from the wildland, into urban areas. And so there's been a lot of work about looking at embers that loft, fairly high up into the atmosphere, a couple hundred meters, and then they transport down, and then they land on some poor guy's roof, and his house lights on fire. Okay, obviously a problem. But there's another mechanism of embers that have received much less attention, and this is what people call ember storms or ember blizzards. So these are embers that don't loft very high; they stay very close to the ground. Okay? They experience a lot of turbulence because they're close to the ground, and they interact a lot more with the built environment around them, well, the built and the natural environment around them, right? They're interacting with trees, fence lines, people's homes, so on and so forth. Okay? And they don't just come with kind of, a few embers here and there. They come in these kind of waves, these big sheets of embers. So these are actual images that you're seeing across the top here. These are real-life ember storms. So they can be created, for instance, when you have a tree that's on fire that suddenly explodes and all these embers just come shooting off it. You get this big sheet of embers coming at you. Okay? And the insurance company is interested in understanding this too for obvious reasons, so they set up experiments like the one you see on the bottom right there. Yeah. So we want to understand how these embers, how they behave, in particular how they move. Okay? And so I'd love to be able to learn some kind of equation for how they behave. And as came up in the introduction, I'm a mathematician by training, so I like PDEs, okay, differential equations. And so I'm going to write down a differential equation for you, but I'll try to keep it relatively light. Okay? So I'm going to have ember locations are going to be the arguments, okay? And there's going to be a rate of change, and then my model is only going to have two things inside of it. It's going to have what the wind's doing and how they spread. Okay? And that's a spread as in disperse or diffuse. Okay? But instead of introducing a new variable, I got this idea from a developer at Julia. To make things lighter, you use an emoji or a picture or something like that. So it's d by dt of an ember storm, right? Is the wind applied to the ember storm plus the spread of the ember storm. Okay. And the simplest wind model, of course, is just putting advection, and the simplest spread model is diffusion. Okay. And so U is going to be the east-west behavior of these embers. V is going to be the north-south, and D is going to be the spread rate. Okay. Now, getting good data for embers, or ember storms in addition, is actually pretty hard. So I started with a very simplified model for embers, and it's purely just simulated. So what I'm trying to show you now is that there's this method out there that we've been using more and more, and Jamaica's working on it, that we can use to be able to learn governing equations from data that we measure in the field, or eventually measure in the field. But when we aren't able to measure it in the field for one reason or another, we can build simulated data and then put that through this machinery and try to see if we recover the equation that we were expecting. Okay? So here I'm just doing a little particle-based method where the quote-unquote digital embers, I guess, or virtual embers, are moving in the direction of the arrow, and then they're spreading with a diffusion coefficient of 0.2 there. So I get all these ember locations, I get all these snapshots of where the embers were at as a function of time. Okay? And I pass this into this framework called Weak-SIMD. And so this was developed by David Bortz, who's actually here, he's at CU Boulder in the math department, and his previous PhD student, Dan Messenger. And so you put it through this framework, and it tells you what PDE governed that data. And it ends up giving us the correct velocity within a couple of percent here, or a fraction of a percent even. So we get the right velocity, and we get the right diffusion coefficient. So this is a nice tool for us to be able to learn equations that we're going to see in a variety of applications in fire science. Okay, So the next problem we're going to eventually apply it to is what you're seeing here. And but first I'm going to talk a little bit about what my student my previous student Darren Sagos, who recently graduated, did. So Darren, Darren has a lot of expertise in cameras and film and this type of stuff, and also experimental work, which is quite rare actually in my department. So what she wanted to be able to do was she wanted to be able to take measurements of dynamics in fire environments, so in this case, a propagating fire line, and be able to build, well, first of all, be able to figure out where that fire line was as a function of time using computer vision type ideas, and then also to be able to eventually learn models, right? Whether they're statistical, and now we're working on physical ones as well. Okay? So this is an experiment we did, or I shouldn't say we, I wasn't there, but Darren did up at Tall Timbers, where it was a very small pine straw fuel bed, okay, about 2 meters by 2 meters. There was a fan that's off the bottom of the screen that's making this a head fire, what you're watching. There's these metal sheets across the side, that's to try to minimize any kind of effect from cross flows. And then mounted up above the fire is a GoPro, which is what you're looking at the results of right now, and a FLIR camera, so an IR camera. Good. So we want to be able to figure out where that fire line is as a function of time somehow, using computer vision type ideas, and then use that information to build models eventually. Okay? I should point out that there is a lot of work on computer vision. Obviously, okay, people like graphics and video game and movie, Hollywood, they all have computer vision type algorithms. The issue that we ran into quite quickly was that the dynamics in fire is just so chaotic, and there's just so much turbulence and all these kind of things that none of these kind of standard algorithms worked. So we had to really build one from the ground up. Okay, yeah.
Just curious, is the small fire a control?
This is controlled. Yes. Yeah. So there was what typically happens when they do this kind of experiment here is they pile on a whole bunch of pine straw, okay, really deep, and then they light it on fire, and you get somewhat of a more intense fire. And then they keep a real close eye on it, obviously, to make sure it doesn't spread. But that burns a nice black spot for you. And then you can go and you can put pine straw inside the footprint of that black spot, and then light another fire, and you don't run, or you help to minimize the risk of the fire actually escaping, because there's no fuel once that new layer of pine straw that you put down. There's no more fuel left for it to once it burns up. Okay? So this whole experiment you're seeing here was about a minute, a little more than a minute. So it was a very short fire. Okay, so this is the type of data that we that we capture from this. So this is looking at the IR camera. Okay, so fire line is obviously up here at the top. Okay, but you can see all the smoldering going on back here. It's still extremely hot. This is black by this point, okay? But it's obviously still very hot. Okay, there's the corresponding, or roughly the corresponding visual pictures of what's going on there. Okay? So we want a way to be able to figure out where the fire line is. Okay, say something that looks like this. Okay, and we want to know where it looks at every time step, and then we want to find a way to turn those fire lines, or those representations of the fire line, into rates of spread or velocities, whatever terminology you want to use. Okay, so this is done through using standard methods in computer vision, but again, we had to make some adjustments and tweaks and some creative ideas to make it work for this environment. Okay, so it does use some of the standard words you'll hear in computer vision. Okay, segmentation and cleaning of the image, edge detection, that's looking for the boundary, and then ultimately you have multiple boundaries at every time step. And then we find we solve an assignment problem, which basically says, how did the fire line that looked like at the last time step, which is here's the red curve, how did it end up looking like the blue curve? Okay? And so this gives you a bunch of displacement vectors, which are the black arrows we see here. You multiply that by the frame rate of the camera, and then that gives you a velocity. Okay? And we take those velocities and we bin them. Okay? And you end up getting something that looks like this. So this is a representation of what velocities we observed over all spatial points where we see where there's fire, and all time points. So there's about 4,000 data points inside this distribution. Okay? And we realize that if you plot it on a semi-log y-axis, you get something that looks pretty linear. Okay? And so the dashed line is showing us, or is showing you the the best fit exponential distribution, and then you can find some error bounds using what's called Markov chain Monte Carlo, or MCMC. That gives you kind of a window. Okay, so that's why you see these two red lines with the purple one going down the middle. Okay? But what I like about this is that we had an experiment where we had homogeneous fuels. Okay, it was all just pine straw. It was on flat ground. The wind was as controlled as you can make it in the environment. Okay. We had those sheets up at the side, so everything was kind of as nice as you could imagine. Okay, these are all the parameters that we put into our models, like Rothermel or something like this. But look at the range of values for the rate of spread that you can have, right? So this really is kind of telling us that maybe using just one value for the rate of spread based on all these input parameters is not the way to go. Maybe we need to think about kind of statistical representations of what the rate of spread is. Okay? So just as kind of a fun experiment to see if that, what would happen if we actually used this distribution to build a rate of spread, we did, it's more or less a level set method, but we have a level set method, so we had a fire line started at the bottom, it's propagating upward, and at every point, to advect the fire line forward, move the fire line forward, what we're doing is we're sampling from that distribution over there, okay? And now I'm not saying that this fire line is, accurate or, correct or anything like that, or any better than any other model or fire line model that's out there. But it does give you some of the features that you might expect, right? You get kind of, you don't get like if you get a nice straight fire line, that's obviously not very physical. There should be some roughness to it. We're getting that kind of behavior. Okay? So this is I think, is an interesting way to think about how to do, rate of spread type models. Okay? And I want to point out one thing about that distribution that you see here, because we're going to come back here in a little bit. So the mean value of that distribution is 4.4, so about 4.5 centimeters per second. That was the average rate of spread of the of that fire line in that experiment. Okay, we'll come back to that, but I want to show that we can do the plume as well. So this was, the fire line was, it had its challenges, but the plume is actually much, much harder. So we wanted to be able to understand the plume dynamics, and in particular, for our project with the Department of Defense, we want to understand what they call the near-field plume. So the plume, very close to the ground here. And so we can apply the same method that Darren developed. It's called FDV. I think I forgot to name drop the acronym. But we can apply the same algorithm to look at the plume boundary, and then do an assignment problem to find the, how the plume was moving, turn these into velocities, turn them into distributions, all the stuff we did for the fire line. So the red and the yellow line is showing you the fire line, or the plume boundary at two different time steps. And then the kind of cyan light blue are a bunch of vectors that, there's so many of them that they get washed out. They don't look like vectors, but that's what they are there. Okay, so we can bin these. And so we can bin them in the downwind, upwind direction. So that's the horizontal velocity. And then we can bin them in the vertical velocity as well. Okay, so that's about plume rise, and then the plume does come back down too. And it doesn't look nearly as nice as what we saw for the fire line. We don't see a nice exponential distribution or a Gaussian or something like that. But we can use this to actually make some predictions about the fire or the near field plume structure. And one thing we can do, relatively easily, is we can look at the mean value of these two velocities. Okay? Again, remembering that the one on the right is about vertical lifting, and the one on the other one is about moving downwind. And then we can look at their ratio to define a slope, and then plot that slope on the plume. Those are the black dashed lines, and you can see it lines up really nicely with actually what the plume is, what the plume angle, right? The bending rate was of the plume. Okay. Okay, coming back to this one. So here's a zoomed-in copy of that same experiment that you that you saw at the beginning of the fire line moving from the bottom to the top, and this is really what Jamaica's been working on now. So we can take that movie and crop it a little bit because I don't want to deal with edge effects at this point. Okay, and I can run it through Darren's algorithm FDV, and you get the moving fire line moving from the bottom to the top. And the question is, can we find a PDE that gives us that dynamic, that moving fire line? Okay. So I'll introduce H to be how far I am from the ignition point, okay? And X to be how far I am from that bottom left corner, basically. Okay. And you can plot that whole thing as a surface. And so that's that plot there. Okay. So here we got here's our x coordinate here, time's running this way, and then how far we are from the ignition point is moving this way. And then when you see it plateauing at the top, right, that's because it ran out of fuel. We hit the end of the boundary, so there's no more fuel for it to burn, so the fire line's not moving anymore. It's just sitting there kind of burning up the little bit of fuel that's left at the end. Okay. So we can take that and we can plug it into that algorithm I told you about before that our colleague at CU Boulder works on. Okay. It's called weak SINDI. So we plug it in there and we see if we can get a PDE out of it. And lo and behold, it gives us a PDE. Okay. So it gives us this PDE with 5 terms on the right-hand side. It's got some nonlinear terms in here. Okay, we actually know the numbers C1 to C5. I just didn't write them out here for you. Okay, and then we can solve that PDE numerically using the same initial condition that we have for the fire line, and you get that shape there. Okay, so pretty good agreement between what actually happened and what our learned model is able to predict about the fire behavior. Okay? And the coefficient C1 that we have here turns out to be 4.6 centimeters per second. Okay? But C1 is just representing, if we didn't have any of those other terms, if C2 through C5 were all 0, that would just be that ignition line moving upwards at a rate of 4.6 centimeters per second. And if you remember, a couple slides ago, I told you the mean value of that one distribution, it was 4.4. So we have really good agreement between what the statistical model is telling us what the mean rate of spread is and what this learned physics-based model is telling us about what the rate of spread is. Okay? But what we've been working on this week, and this is really, really preliminary now, moving on this next slide here, is that C1, this rate of spread, really kind of washes out everything else. Okay, so the weak SINDI is trying to fit the data to some kind of model, and it's realizing that it can do most of the work with C1, but then it gives us the C2 through C5 as well. But they're just not. I can't trust them as much, right? Because C1 is really dominating. So what we've done is we've said, well, let's just subtract the mean value and think about the fire line fluctuations, okay, which I'm calling H tilde here. So now this is like the frame of reference. You're moving with the fire, basically, and you're just seeing the fluctuations of the fire line. Okay, so I'll let it run once more there. Okay, that gives us a new data set. Okay, it looks like that. Okay, it doesn't look quite as nice as that last one, but again, it can go into weak SINDI. Okay, no problem. It'll give you a PDE. Okay, and there's the PDE for it. You can see that there's no constant term anymore because this solution doesn't transport anymore. We subtracted the mean value. It's just jiggling around. It ends up only having 3 terms, and we can say a few things about a couple of those terms. So first of all, the number C2 is negative, and that means that we have an exponential decay in these oscillations. So they're getting smaller and smaller with time, and it also sets a time scale for you. It gives us an e-folding time of about 36 seconds. And then the number C5 is a nonlinear advection term, or it's exactly the nonlinear term that shows up in Berger's equation, which we know does things like introduce shocks and rarefaction waves. So this would be like the fire line, coming together to create sharper interfaces or spreading out to smooth them out. Yeah. So we're starting to see some kind of interesting, things going on here. Okay. All right. I think this might be my last time switching gears. Okay. So this is this is what I worked on with my postdoc Xin Tong, or my previous postdoc Xin Tong. So Xin came from a background of AI and deep learning and all these types of tools. And so what we wanted to be able to do was see how much data is actually needed to be able to train different networks for fire science type applications. Okay? So when you think about kind of people that do deep learning, something that they quite often have a lot of is a lot of data, right? You think about the medical imaging type profession, right? They have a gazillion MRIs or whatever, right? So they're able to train these models. Okay? Fire is not so, it doesn't really have this advantage, right? There's not nearly as much kind of nice, clean, labeled data that doesn't have a lot of noise inside of it. Okay? So, but nonetheless, we wanted to see kind of how much data is needed to do these types of tasks. And so the problem that we came up with was, let's see if we can predict what's called the first arrival time map, which is for every point inside my burn unit, when did I first see fire? When did I see fire for the first time? Okay? So this is a first arrival time map here. Fire started here, then it shows up in the blue region, then in the red region, and then ultimately out in the yellow region. So we wanted to be able to train models that take in, standard fire inputs, things like, the fuel behavior, the wind, so on and so forth, and outputs first arrival time maps for us. The issue is that we don't have enough data. So we used we used simulated data. Is basically what we did. Okay? So we had a code that would let us tune different parameters on the fire behavior. So the parameters it could control is things like background wind, fire intensity, fuel burn time, the ignition angle, and a random stochastic term. Okay? So 5 parameters went into it. And so we train these types of models, and you're looking at one of these particular models here. This is called a UNet model, but it uses kind of some of the standard AI type AI type operations people do, right? Convolutions, pooling, concatenation, these types of things. Okay. So we had 3 different models. So there are so the left is the ground truth. So this is an example of a first arrival time map that the trained model had never seen before. And then we looked at the 3 different models, okay, CNN, UNet, and FC UNet, and we look at how well of a job they can recover what we're expecting to get the ground truth. Okay? The CNN has all sorts of kind of, it can't resolve these kind of sharp interfaces. It's got all this kind of, blurry stuff going on. So we don't like that one. UNet and FC UNet actually both do a pretty good job. Okay? They have actually comparable errors. When you look at the errors down here, they're both around 25 seconds here in the root mean squared error. But the difference is that the network for FC UNet is much simpler. Okay? It has a lot fewer weights inside of it. In particular, it's got about 1/3 as many weights, about 500,000, whereas the UNet has about 1.5 million. Okay? So requires a lot less storage to be able to store a network like this one versus the one that you see in the middle there, or the one labeled UNet. Okay. And then the bottom right plot is showing you kind of the standard thing that we look at in when we think about deep learning, which is about how does the error decay as we go through the training process. Okay. So this is what this kind of curve is what you expect to see, and that's what we got here. Okay. So that's the forward problem, but the real problem I was interested in was the reverse of this, the inverse problem. Okay. So if you knew the first arrival time map of a burn unit, so you knew when each pixel first saw fire, could you figure out what the wind was doing? Could you figure out what the fuels were? Could you figure out how intense the fire was? All these kind of things, right? So that's going the other way. Okay, so you start with the first arrival time map. Again, you put it through a big network, okay, and out will come some parameters. Then you can take those parameters, you can plug them back into the idealized model to see how well of a job you did at figuring out what the parameters were. And when you do that, you end up getting the one that you see there in the middle, and just comparing the one on these 2 first arrival time maps, at least to the naked eye, they look actually fairly close. We've done a good job of being able to, to parameterize or build a network that can parameterize the inverse problem. Yeah. But it's not perfect, and in fact, it's actually a lot worse than the forward problem. We can only get errors on the order of about 20, or about a little bit less than 20%. But this was fully to be expected because it is an inverse problem, and inverse problems in general are, well, because they're inverse problems, they're much more sensitive to noise and these types of problems. Okay? So we weren't too surprised that this kind of thing happened, but I think it's a nice idea that lets us take first arrival time maps and figure out parameters, and it also lets us try to quantify uncertainty in parameters. So we can say which parameters is it most sensitive to by looking at it within this light. Good. Okay. I guess I do. I'm not going to talk too long about this one, but this is just kind of a fun project. So this was a field school class that we did a couple of years ago, and where the students were tasked with coming up with experiments where they would that they could do in the field and take measurements with, and then analyze the data and so on and so forth. And so Jamaica, my previous postdoc again, Shin, and I we're interested in understanding some of the, or combining kind of two fields that I work on. So one is obviously fire, but the other one is more erosion and hydrology and groundwater flow and stuff like this. So what we wanted to understand was the thing we see kind of all the time out here in the when you have fires in mountains. Okay, you get fire goes through a unit or goes through a landscape, and then at the next big rainfall, what do you end up getting? Right, you get massive landslides, rock slides, all this kind of thing. Okay, and so people think this happens because when the fire goes through the landscape, it actually changes the it changes the vegetation, it burns up root systems, all this kind of stuff. Okay, and this can lead to erosion when you end up getting rain. So what we wanted to be able to do was burn a small pine straw table here, or burn a table with pine straw on it, put water on it, collect that water, and look at the chemical composition and the sediment, the amount of kind of soil that was collected in that water when we have two different slopes. So we could pitch that table at different slopes. We could either burn the unit or not burn the unit, or we could have different fuel types different soil types underneath the pine straw. Okay. So there's the burn table. Okay. There was a big PVC support system that we built. It was pretty rickety, but it it made it. There's a ladder that's zip tied to a broom, which is holding the whole thing up, because we of course had to get water up there, so you could see the clear tubing there. That's running water up to the top. So it actually sat there really nice. And then as soon as you turn the water on, it would just go, right? And so that's why we had to jerry-rig that with what we had to set that up there to so that the whole thing didn't come collapsing down. But we did it, and it worked. Okay? We collected runoff water down there. There's a zoom in of the system from a different angle, so you can kind of see how the water is going to funnel down the table. It hit a collection basin there, and then it got filtered down to that Rubbermaid you see there at the bottom. And then we collected that stuff and that water, and we filtered out the amount of sediment in there, and based on whether it's burnt or unburnt, and what kind of soil you had, and whether it was a low slope or a high slope, you get different amounts of sediment. Okay, but I'm not going to say anything concrete about the numbers. Okay. All right, so where are we going from here? So Darren is still working on using her FDV method to be able to make some characterizations between the flame sheet and the plume, so right where the flame and the plume are meeting each other. And then we're also using the Cindy method that we've used so far only for looking at how the fire line propagates and also how that toy ember problem was. We'd like to be able to learn how plumes propagate. And so we have very, very preliminary data again here on the bottom left. So this is from a GOES satellite. This is the LA fire that we had in, I guess, January or February of this year, where we are using FDV to try to figure out where the boundary of that plume is. We're not doing a very good job until about now, okay? But now you can start to see we got this moving interface. And so what I'm hoping to do is learn governing equations for how this interface that separates the plume from the fresh air, how it evolves, right? So that we can say things about, its dispersion and its transport and so on and so forth. Okay? So there's a list of kind of all the papers that that came out of myself and my co-authors today, and then the Cindy one there is written down on the bottom. And just to wrap up, I will throw this up. So this is an augmented reality sandbox that we have at FSU. I'll just, I'll give it a 30-second plug. Basically, what you can do is you can make, in real time, you can make adjustments to the elevation of you can move the sand around. So you can, build mountains and valleys and stuff like that. And so this is a previous student, David. He's going to start putting some water in there. And then he will, so he's going to maybe fill up the volcano there at the top, and then you can break it, and water rushes down. And so it's kind of fun to play with. But what David really did with it was he put a fire model on there so that you can you can use it as kind of a teaching tool or to, for doing kind of simple experiments about how fire behaves in regions with topography. So this is, I'll let it, it's a couple minutes long, so I'll let it play, and I will be happy to take any questions. So thanks so much for listening.
Thank you for that really nice overview of all your research on fire. We'll take questions. And we also will take questions online too.
Thank you, Brian. Very nice overview. I have a question with that plot that you have with the exponential feed that you got.
For the rate of spread?
Yes.
Yeah.
So then that one you saw on the right when you randomly sample from that distribution and you put it there. So my question is, for a given point, is there correlation with their neighbor? So you see what I mean?
Yeah. No, there is no correlation
No
whatsoever.
correlation
There's no
at all.
correlation whatsoever. We are just sampling. That distribution was over all of space and all of time. That's how it was built. And then that gives us an exponential distribution. And then at every point, I'm just sampling from that distribution to get a rate of spread, and I apply that rate of spread to that point.
But in reality, that
Yes.
distribution comes with neighbors.
That's right.
So
Absolutely,
You
it
can
does.
do.
Yep.
Technically, you can do it, right? So.
Sure. Yes. You could sample differently from that distribution where you have some kind of bias that says if my neighbors were these values, then my value should maybe be similar, right? Because you expect that the fuel beside you is maybe similar to the fuel that you're sitting at. So yes, you could do stuff like this. It was really just kind of a exercise to see what would happen, and it looked cool, and so I like to throw it in the slides to try to drop that seed in people's minds about thinking about the rate of spread as a distribution instead of thinking of it as a deterministic, semi-empirical but deterministic model, such as RAL uses for how fire spreads.
Yeah. Thank you.
So on that topic, I wonder if, like, for modeling that in a sort of physical model, like word fire, I wonder, we currently have the RAL parameterization. So if that gave you the mean or the base value of the fire spread, and you would perturb then that result with some sort of distribution that would relate to that, do you think that could work?
I do. I don't know what else to say besides that. Yeah, I think that's an approach that people should think about. So yes, I am. I've been talking with Pedro lots this week about WRF and how you guys couple it with RAL. And so yeah, I'm imagining a situation where maybe it could be as simple as you don't just use the RAL value that you get that comes from the wind and the fuel or whatever, but you sample from a small distribution around some small variance, right? So you don't just you don't always just use one deterministic value. You say, well, there's some uncertainty in that. So instead of just picking that value, I'm going to pick something from a distribution centered about that value.
Yeah, and then we could use that kind of data to define what is the distribution.
That's
and
right.
what
That's
is the
right.
standard
That's right. How much
deviation.
variance there is and all this kind of stuff. Yeah. That's my hope that this kind of that I have or other people have kind of moving forward with these types of models. It's right beside you.
Oh, sure. Do we want to do the online question?
After you.
Yeah, really nice talk, Brian. Thanks. So in terms of the distribution that you showed of the rate of spread, like physically, what are the pieces that are contributing to that, right? Like small scale fluctuations in the flow, the distribution of of the fuels.
That's
and
right.
So
That's
maybe
right.
you can say something
Yeah,
about that?
so we weren't, of course, it was still a outdoor experiment. We did our best to spread the fuel homogeneously, but at the end of the day, it was, you just pick up some pine straw and people just start shaking it, right? And so you try to build it as uniform as you can. But yeah, so I expect that, the fact that you have maybe this could even tie back to what I showed at the very beginning about the fact that you have the porous media structure. That's going to really affect how air gets into and out of it. And when we showed that experiment, we're talking about flames that are, like yay high or something like that, right? So if it was a huge flame, then I think probably you wouldn't have seen as much variation. But because you have little flames and you got air kind of sneaking in through all these crevices, that's going to have a big effect on how on giving you a lot of variance or variation in the rates of spreads that we measure.
Yeah, and just a quick follow-up.
Yep.
I'm curious what your plans are for just future like burn experiments like that, and like different fuels, and like repeating the same experiment, right, to see like how robust the distributions are and things like that.
Yeah, so so Darren did do some work where she tried to look at, or I shouldn't say she tried to, she did look at some different experiments. She collected different data, and some of them were at the Jones Center. So one was at a consortium that was up in Kentucky. I can't remember the details, but she used a drone actually. And so we've been trying to use drone data as well to be able to make these types of measurements. There's new challenges that come in with drones. So that example that I showed you there, that was in a nice empty field where they just put the pine straw in the middle. When you have a drone flying over top of an actual prescribed fire happening, of course there's trees. So you got to deal with this type of stuff. You have to try to figure out where the fire line was when it's hidden below a tree. The drone is of course moving, so you need to try to correct for that. So there's a lot more that needs to go into it in that direction. So she's a big loss to the group.
Okay, so we have a question online from Darren Clabo. Can your methods be applied to spotting potential ahead of a fire line?
So I'm not sure exactly what method he's referring. Maybe he's referring to the, feel free to update it there. But if we're talking about the stuff we've been talking about for a while, where we're using FDV and so on and so forth, yeah, we have been trying to do some work on building models for fire spotting that has again, a statistical element to it. So there's actually been a lot of, there's been work where people looked at distributions of where embers land, how far they land, what their burn time is, all these types of things. Okay? So you have all these kind of distributions that have to work together to end up with fire spotting, right? The ember has to be lofted, it has to stay ignited, it has to land on a fuel that can burn, it still has to be burning when it gets to it, it has to have enough thermal energy, so on and so forth. So we have been thinking about kind of developing statistical models for the embers, but that's it's work to come.
Is there anybody else have a question?
I'm here till Friday.
Yeah, so about the embers, and so how are you considering that there is a distribution of certain sizes or masses, or
Yeah.
what do you take into account?
So we have very, very new work on embers where we are absolutely taking into account their sizes. We're taking into account the billows that are inside of the plume itself. We're taking into account the density, these types of things. But I didn't talk about any of this stuff today whatsoever. The only ember stuff that I really showed you was really that using that very, very simplified model where I had the little circle of embers that were just moving down that black arrow and spreading at the same time, right? So that's all we've done with the ember so far. Where I'm envisioning that going, and what I didn't go into details with that particular that application of Cindy was actually I didn't track individual embers. What I did was I turned it into a mean field. So I built a distribution of embers. So where I'm saying, there's a certain density. So basically you're solving for an equation about the advection and the transport of the density of embers as they move forward. So it gives you a nice continuous representation of the embers. And so that's the direction that I'm imagining the ember work going for us. And then it's kind of tough to think about, things like size and fuel composition, but I know these are all important things, right?
Well, I think you and we should talk more.
Okay, I'm here tomorrow. Yeah, I don't fly out till Saturday afternoon.
I'm looking from a different perspective, actually the particle perspective.
Okay.
And so I think that it can be very holistic to have more conversation and more interaction.
Okay, that'd be great. Yeah.
Just curious, have you thought about like the necessary resolution that's required from the observational perspective compared to the fire line size in terms of like what you can what you can back out as like an accurate representation of like the fire perimeter tracking? And the reason I ask is just because I feel like there's such limited measurements, right, of all of this, and people try to take a satellite approach, but oftentimes it's just like too coarse spatially. So I just wonder if you like have any like thoughts about like the resolution differences, right?
Yeah. So we've absolutely thought about this. I didn't throw out the numbers, but the one burn I did show you with the two sheets at the side there, with the resolution of the camera and where it was located. The resolution of a pixel was about 1 centimeter. So it's very, very kind. Satellites can't get anywhere near that, of course, and not even drones can't even get there either. So it really relied on the fact that the camera was only about 30 feet in the air, or 50, I don't know, 20 feet, 30 feet in the air, or something like that, and was of decent quality. So yeah, we are looking at when I talked about the rate of spread, it showed you that distribution. I should have pointed out that this is looking at rates of spread of points on fire or little pixels on fire that are about a centimeter by a centimeter squared, right? And maybe that's not so important when we're thinking about, large scale fires that are moving out through the west here, right? So I don't know if that answers the question or.
Yeah, it does. And I'm just wondering maybe like if you artificially coarsen your observations, like how your results start to change.
Does the distribution look different, for instance? So we did do that, but we did it in time, not in space. So we sampled at different rates in time and looked at how the distribution changed, and then we made some arguments using Shannon sampling theory about this is the appropriate time scale that we should be looking at to recover the correct physics. So there is kind of theory and analysis that can be done to figure out what the right scales are to look at. We really did it over time. We haven't done it over the spatial scale. Yeah.
Thanks.
Yeah.
We do have a couple more minutes for questions, if anyone else has any questions. I will say that, as David alluded to, that he'll be around through tomorrow, so second floor. And I can just get in contact with Pedro or myself, and we can help you get in touch. Let's thank our speaker again for taking time to speak with us.